Okay, here's our third and last video for section 5.1. And so we are asked to use rectangles to approximate the area under the curve y equals 2x squared plus 5 from 0 to 6. And they told us to use these partitions from 0 to 1, 1 to 3, 3 to 5, 5 to 6, and the midpoints of the subintervals. So I chose this example to illustrate you do not always have to have widths of equal length. In the past examples that we've used, all of the widths were the same. We had regular subintervals. Here we don't, so you don't have to. It's okay if you don't. So let's just see what kind of area estimate we get. They tell us to go from 0 to 6. So on my little chart, let's see. This is 1, 2, 3, 4, 5, 6. I have to go from here to here. So if we were going to do regular subintervals, you could go by 2s or you could go by 1s. But they said the first one's going to be from 0 to 1. 0 to 1. So here's going to be my first one. And then from 1 to 3, here's my second one. So you can see already the width of this guy is not the same as the width of this guy. And then 3 to 5. And then 5 to 6. Okay, there's the little rectangles, how they're going to be split. But then it says use the midpoints of the subintervals. So halfway between 0 and 1 is here, and this is where it hits the curve. So that's at 0.5 is where I let the height be. Halfway between 1 and 3 is 2. So I go up to here, and this is where I let the height be for this second subinterval. And halfway between 3 and 5 is 4. So I go to where 4 hits the curve right here, and I let that determine the height of my rectangle. And then halfway between 5 and 6 is here, and this is where it hits the curve. And so that, let's see, let me get that a little better. Halfway between 5 and 6 is here. So that is where my height is going to be for my last subinterval. All right, so we got 1, 2, 3, 4 subintervals, but they are not the same width or height. So let's add these up. The area of the first rectangle is the width is 1, and the height is f of 0.5 because we went by the midpoint. All right. And then the second rectangle has a width of 2, and the height is, we went with the midpoint, f of 2. And then the third one has also a width of 2, and the height was the middle point, f of 4 was the middle point. And then the last one had a width of 1, and f of 5.5 was the midpoint. 5.5. So maybe I shouldn't call these, there's so many numbers. Maybe I should call this something like A, B, C, D. The area of, this is the area of rectangle A, B, C, and D. So we're just going to add that up and get the estimate of the area under the curve. So you could do the same thing here. You could plug these numbers in, 2x squared plus 5, and what do we need? 0.5, 2, 4, and 5.5, and figure out what those are. I did that. I didn't write out what they were. Oh yeah, but when I multiply 1 times f of 5.5, I got 5.5. I got 26. I got 74, and I got 65.5. And when I added all this up, my estimate for the area under the curve with these subintervals was 171 is what I got there. All right, so now we're going to do one last thing, and we're going to look at the distance problem. So let's see. Distance is equal to rate times time, right? Or velocity times time. So if you think back to the first part of this course, we were concerned with velocity. And so what we did was we looked at the rate of change of distance with respect to time, and that's what velocity was, or we looked at the derivative. This time we're going to look at velocity. If we know the velocity and time, we're going to come up with the distance. So in a sense, this is an inverse process of what we did before. So here it is. Let's look at this situation right here. It says, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them on the following table. What we want to do here is find the lower and upper estimates. Find the lower and upper estimates of the distance traveled over this 30 seconds. All right, so let's look at this. This means between 0 and 5 seconds, this is the first interval. That's our first 5-second interval. Then between 5 and 10 is our second one. Between 10 and 15 is our third one. Between 15 and 20 is our next 5-second interval. 5-second interval, 5-second interval. So we have 1, 2, 3, 4, 5. We have 6 little sub-intervals. So let's estimate let's look at the lower one. The lower estimate. Alright, so we're thinking distance. Remember, distance is equal to rate times time or velocity times time. So if we want a lower estimate, we're going to go with the lowest velocity that we see in this first between 0 and 5 seconds. So the time in all of this is 5 seconds. So we have 5 seconds. I'm going to do this 5 seconds times what's the lowest velocity we see between 0 and 5. 25 is smaller than 31, so I'm going to say 25 feet per second. I'm not going to write the units on the other ones, I'm just did it on the first one. Plus the time is 5 seconds times the second interval B between 5 and 10. What's the smallest velocity? 31. Plus the third one between 10 and 15, it's a 5-second span. But what's the lowest velocity? 35 is smaller than 43. 5-second interval, 43 is smaller than 47. 5-second interval, 45 is smaller than 47. The last 5-second interval, 41 is the lower. So if we pick the smaller velocity, we're going to get the lower estimate of our distance. And if we add all of this up, we find that we traveled 1,100 feet. All right, let's do an upper estimate of the distance traveled. It goes like this. It's the same 5-second interval, only this time we're going to pick the higher velocity because we will have traveled further. So, first second interval A, 5 seconds, pick the higher velocity in that span, 31. Plus 5 seconds, pick the highest, 35. 5 seconds, pick the highest, 35 and 43, 43. 5 seconds, 43 and 47, 47 is higher. 5 seconds, 47 and 45, 47 is higher. 5 seconds, 45 and 41, 45 is higher. By picking the highest velocity in that 5-second interval, we're going to come up with the upper estimate of the distance traveled, and it's 1,240 feet. So the actual distance traveled is somewhere in between these two. All right, let's just see. how this relates to what we were doing to area under a curve. We could actually plot this. Let's see, we could draw a graph where we let the x-axis be time in seconds, and we let the y-axis be velocity in feet per second. And it's 5-second intervals. We could go and mark this off in 5, 10, 15, 20, 25, 30. And we could mark this, let's see, it goes up to 40. We could go 10, 20, 30, 40, 50, 40, 30, 20, 10 feet per second. And we can plot these points. At 0, we're at 25. And at 5, we're at 31. And at 10, we're at 35. And at 15, we're at 43. And at 20, we're at 47. And at 25, we're at 45. And at 30, we're at 41. 41, maybe there. Okay. We could connect these. And we could estimate the area under the curve right here. And the area under the curve right here would be the distance, an estimate of the distance traveled. So it's the same problem, because time, we'd be multiplying time, right? This width is time, and this height is velocity. So what we just did here, when we did the lower estimate, was we went with the lowest point that we saw in each of these, right? And then when we did the upper estimate right here, we did the highest point that we saw. We did the upper estimate. Whoops, that didn't go good. We did the upper estimate right there. That's what these calculations were. So we see that the area problem is the same thing as the velocity problem, and the distance traveled is equal to the area under the curve. In fact, each rectangle can be interpreted as a distance traveled during that 5-second interval. So this is the end of section 5.1.